Okay, welcome to the second lecture of thermodynamics, in which as usual we shall start with recapitulation. So, we discussed thermodynamic variables which are macroscopic objects measurable in experiments. There are of two types, one is extensive and other intensive. Extensive thermodynamic variables are indicative of the system size. For example, number of particle, volume, internal energy. Later we will introduce probably concept of free energy, entropy. These are extensive variables. They are indicative of the system size. If we double the size of the system, maintaining equilibrium, these quantities will be doubled. On the other hand, pressure, temperature, these are intensive variables. These quantities do not depend on the system size, okay, insensitive to the system size. They are fixed by the equilibrium condition. Similarly, if I have density which is n over V, this quantity is an intensive quantity even though n is extensive and so is V. So, these extensive and intensive variables are my thermodynamic variables which describe a system. But the system which I am considering is always interacting with a reservoir, or we called it the rest of the universe or simply the universe. So, system separated from the universe by walls. We talked about different type of walls. For example, adiabatic wall which does not allow any heat exchange, or diathermic wall where I can have heat exchange. In general, I can have both heat exchange and mechanical interaction. So, system, universe and system is separated from the universe by wall. System is small, whereas reservoir is very big. I can assume that heat capacity is infinite, which I mean by saying that if I extract heat from the reservoir or I release some heat to the reservoir, its temperature does not change. Okay? So, as I said, walls are diathermic and adiabatic. In general, we will consider walls which are diathermic and also movable, so that I can do some mechanical work on the system. On the other hand, system can also do some mechanical work on its own on the universe. So, two types of interactions I mentioned, mechanical and thermal. There could be other type of interactions. For example, there could be particle exchange, which we are not interested in the present set of lectures. Then the concept of equilibrium. Okay. Equilibrium means all the thermodynamic variables we measure do not depend on time. This is an idealized concept. All these walls, there is no perfect adiabatic wall in this universe. Okay? This is an idealized concept. Similarly, equilibrium is an idealized concept. Okay? I would rather say I define equilibrium within the time scale of my experiment. As long as I am doing experiment on the system, the thermodynamic variables, pressure, temperature which I measure, they do not depend on time. To maintain the equilibrium, whatever change I will do is a quasi-static change. Quasi-static change means it is a very slow change, which means it is slower than all other time scales of the problem. I can assume that every instant of time my system is in equilibrium. I can describe, if I have an ideal gas, rather 1 mole of ideal gas, I can describe it through the equation of state PV is equal to RT at every instant of time. That explains what I mean when I plot a PV diagram. If I plot P as a function of V, I get a PV diagram which says at every instant of time I am in equilibrium. I can write PV is equal to RT. Okay? So, quasi-static process is very, very important to maintain equilibrium, and since I am maintaining equilibrium at every instant of time, I can write the equation of state. Okay? This is brief recapitulation what I did, the concepts of thermodynamics. I repeat, it is a macroscopic subject, but eventually the results what we get at the end of the day will be same as those which we obtained from kinetic theory of gas. Okay, let us proceed. So, I proposed first law of thermodynamics for you, is a conservation of energy. So, I can have a situation where I have my system and I give some energy to the system in the form of heat. So, I provide an energy which I will call thermal energy amount delta Q, or I use this notation delta Q. Whenever I write tilted delta or Q delta, it represents an infinitesimal change. Let me call it a finite change, but let me not bother about these nitty-gritty details. We use these two notations almost interchangeably. Okay? So, I supply delta Q amount of heat to the system, and if I do not allow the system to do any mechanical work, some quantity must increase, and that we call the internal energy. Internal energy must increase because energy cannot be dissipated. If energy cannot be dissipated, some quantity must increase, and that is the internal energy. Let us say we have ideal gas, and it is the internal energy of the ideal gas that will actually increase if I provide delta Q. Similarly, if I have a system and I push this wall of the container, I am doing some mechanical work on the system. I am doing some mechanical work. I will always assume there is no friction, there is no dissipation. That means all I am doing is conservative. Okay? Okay? If I do some work, again there will be increase in internal energy because I am not allowing any heat exchange. These two are the extreme situations which tells me that I have to bother about three quantities. One I have already written delta Q, that is heat exchange, and then mechanical work delta W, and I mentioned something like a ghost that appears in our theory now, that is the internal energy, which I write as delta U, okay, which I write as du. So, I have delta Q, delta W and delta U. The first law of thermodynamics, which is nothing but the conservation of total energy, will involve these three quantities. This should be very, very clear. So, I must take into account the internal energy. We will restrict to two hypothetical extreme situations in which one of them I have only heat exchange, in the other I only have mechanical work. Okay. Having said this, we proposed the first law of thermodynamics. Delta Q is the heat supplied to the system, delta W is work done by the system. So, delta Q should be equal to delta U plus delta W. So, whatever heat I supply to the system will be dissipated in two forms or will be used in two forms. One is system will do some work. So, this is the work done by the system, work done as I have written already. Let me write it again, work done by the system and this is the increase in internal energy. So, this is how I propose my first law of thermodynamics. All these three quantities delta Q, delta W and delta U, they should be put together to get a conservation of energy. Now, if you look at this equation, first extreme case was no delta W. So, case 1 which we studied in the previous slide, there is no delta W. So, you see delta Q is equal to delta U. That is what I was trying to emphasize, that if there is no work done by the system, this whole heat I have supplied to the system goes into increasing the internal energy of the system. On the other hand, case 2, which I will soon show what is that case, if delta Q is equal to 0, delta U is minus delta W, which tells me that if system does some work, then delta W is positive, okay? Then delta U is negative because this quantity is positive. If this quantity is positive, delta U is negative, which means the internal energy of the system must go down. System is doing some work at the cost of its internal energy. On the other hand, if I do some work on the system, then delta W becomes negative. Because of this negative sign, delta U is positive. That means I am doing some work on the system and its internal energy goes up. So, this is consistent with whatever we have discussed so far. This is the first law of thermodynamics. And then I briefly mentioned what is an internal energy. Okay? Internal energy, if I consider ideal gas, internal energy is proportional to temperature. Okay? This I have not proved, but for an ideal gas, its function of temperature proportional to temperature. If I increase temperature, internal energy goes up. This constant has no relevance. Kinetic theory has already taught us that average kinetic energy of the molecule is related to the temperature. So, internal energy, if you consider monoatomic ideal gas molecules, then this quantity Cv takes care of counting the degrees of freedom, and we already know in kinetic theory average kinetic energy is related to temperature. So, if you talk about ideal gas molecules, your internal energy is simply translational. If it is monoatomic, it is translational, vibrational and rotational if it is diatomic or polyatomic. Okay? So, it is the internal energy means the energy I was talking about in kinetic theory if I consider ideal gas molecules. Who takes into care the fact that it could be monoatomic, it could be polyatomic, that is in Cv. We calculated Cv elaborately using equipartition, and that equipartition tells us that whether the molecule is monoatomic, diatomic or polyatomic goes into calculating the number of degrees of freedom, and that is reflected in the specific heat capacity. So, this is the internal energy. And second quantity is it is extensive, that means if you double the size, double the number of molecules, definitely it will get doubled. So, it is an extensive quantity as I said in the beginning. So, internal energy is extensive quantity. Secondly, I want to bring a very important notion here. It is a state function. What do we mean by state function? State function means if I go from a state which is characterized by Pi, Vi and Ti to a state Pf, Vf, Tf by means of any thermodynamic process. Okay? I will define the thermodynamic processes for you in couple of minutes. This internal energy only depends upon the initial and final state thermodynamic variables. It depends upon the values of thermodynamic variables which is initial and final. Okay? It does not depend upon the thermodynamic process which is involved in taking the system from this state to that state, which is very, very important. So, it is a state function means it is determined by the thermodynamic variables of a state. Okay? For example, in ideal gas, if you see it is proportional to temperature, if I make a process in which my temperature goes from Ti to Tf, so change in internal energy will be simply Cv Tf minus Ti. It does not depend how I have achieved this process in going from Ti to Tf. Okay? This is very important, it is a state function. But Q and W not. So, heat absorbed or work done by the system, they are not state functions, they are functions of the process. Okay? So, as I have written here, delta Q, delta W, and that is why this delta not D, delta Q, delta W depends on the path thermodynamic process. Okay? Soon we will explicitly calculate them and show that they indeed depend on the thermodynamic process. Du does not. Okay? It only depends on the initial and final state as I have calculated here. So, this is a very important notion and there is a connection between mechanics. Okay? We have already seen adiabatic process. This is how thermodynamics brings in the concept of state function or internal energy. If you have an adiabatic process, okay, so in an adiabatic process you know delta Q is equal to 0. So, there is an work done by the system or I am doing some work on the system. If I say that there is no friction, there is no dissipation, what do I have? I have a work which is conservative, This is very, very important. So, I am doing a work which is conservative. And now, let us recall our mechanics course. In mechanics, we already know in a conservative force field, work done does not depend upon the path I take. For example, if particle in a gravitational field was initially here, I take it here. I can take it in many possible ways, as many ways you like. Someone can take it just vertically upward, okay? But the work done in all the processes are same, does not depend on the path, rather it depends upon the difference of one quantity in the final state and the initial state. That quantity I called potential in our mechanics course. Okay? So, potential work done in a conservative force field is, work done is just the difference in potential, Please note that what I am referring as potential is nothing but the so-called potential energy, or rather I am using the term potential to denote potential energy. It doesn't depend on the path. And if I do a work in a closed loop in a conservative force field, I start from here and I come back to this point, net work done is 0, because I come back to the same position, potential is the same, so change in potential is 0, that is why my work done will be always be equal to 0. So, this is from mechanics, and you see in an adiabatic process work done is path independent, it does not depend on the path because it is a conservative force field, and that gives in the idea of internal energy. So, if you remember, if you understand how do I get the concept of potential in classical mechanics, you immediately get what is internal energy in thermodynamics. Okay? So, it is a state function, ideal gas, as I have mentioned already, du depends on initial and final temperature, because it is a function of temperature only. So, if you understand what is a conservative force field and how do we get the concept of potential in a conservative force field, you immediately get to realize what is internal energy in a thermodynamic process. Okay? And for an adiabatic process, it is clearly a state function if you consider ideal gas, because I told you in an ideal gas it is just CVT plus some constant. This constant has no relevance. In a sense, we are interested in the difference of internal energy, as in mechanics we are interested in the difference in potential. So, this is the first law of thermodynamics for us. This is the meaning of internal energy. I talked about two extreme processes. One is completely adiabatic, only mechanical work is being done. Other is process which is diathermic, in which I allow heat exchange, but general process involve both. One is heat exchange, other is the mechanical work. Okay. Now, this is the question, since I have been talking about work so much, what is the work done by a gas? Well, I will always assume quasi-static process. That means, at any step, at any instant of time, I can use my ideal gas equation. I will always be considering ideal gas, not van der Waals gas at any point on time so far, if not otherwise mentioned, it is ideal gas, could be 1 mole, could be n mole, but I will always assume quasi-static process, so that at any instant I can use the equation PV is equal to nRT. So, what is the work done? Let us assume that there is a container, there is some pressure, some P, and there is a small shift dx. This is the area of the cross section, and there is a pressure P, let us say. Okay? Now, what is the work done? Work done, I know, force into displacement. So, I am just looking at the magnitude of the work done. So, work done should be force, which is pressure times area, which is dimensionally consistent, and dx is this displacement of the wall of the container. Let us say, for example, for simplicity, we are taking a rectangular wall. Okay? So, it is displaced by an amount dx. This is the work done, which I can write as PdV. So, I have expressed everything in terms of pressure and volume, one intensive and one extensive thermodynamic variable. So, what will be the net work done? Net work done is integral PdV from V1 to V2. So, I am assuming that initially I was as a volume V1, then the volume of the system increases or decreases to V2. Okay. I am doing this change quasi-statically. So, this is the work done. Now, if I recall my PV diagram, this is PV diagram, let us say. So, what does it imply? I am integrating PdV. This is my initial volume V1, this is my final volume V2, and this is the work done. So, work done, it is simply the area under the curve in this PV diagram. Okay? So, we have to calculate this area under the curve for different thermodynamic processes. So, this is our next aim, and this will take some time, and we will try to understand the physical meaning of every process. So, we will do it for different thermodynamic processes. Okay. So, let us consider for simplest thing isothermal process. What do you mean by an isothermal process? Temperature is fixed, T fixed. Immediately you already know one thing, if temperature fixed, I am talking about ideal gas, du is equal to 0. There is no change in internal energy, because in ideal gas internal energy is just the translational kinetic energy. If I consider monoatomic ideal gas molecules, it is just translational and it is proportional to temperature. If temperature is kept fixed, du must be equal to 0. Now you want to calculate this quantity, and you know, since it is a quasi-static process, every instant in time you can write PV is equal to nRT, so that you can write this integral as I have written here clearly as nRT V1 V2 dV by V. Okay. All I have done, I have substituted for PV here, PV is equal to nRT, which gives me P is equal to nRT over V. Okay. If I substitute it back in this equation, I simply get this form, and now I can integrate from V1 to V2, this gives me this expression. So, in an isothermal process, this is the work done, there is no change in internal energy. So, whatever heat is supplied to the gas will be converted to work done. If I give delta Q amount of heat, system will do this much of work, because there is no change in internal energy. So, entire heat supplied, whatever I have supplied to the ideal gas system will go into work done by the system. So, this is an isothermal process. Important is du is always 0. I am considering ideal gas molecules. Okay. Quickly I will go to the next process. Isobaric, again what does it mean? Isobaric means pressure is constant. Pressure is constant, which means I will go from a state P Vi Ti to a state P Vf Tf. Okay. It is my ideal gas system. Okay. Initial pressure and final pressure is the same. There will be a change in temperature and volume. That is what I need to calculate. And this expression will be different, and du, internal energy, change in internal energy is there in this process. I cannot say du is equal to 0, rather du not equal to 0 in this process. So, in an isobaric process, du is not equal to 0. Remind you all the time that this delta Q and delta W depend on path, that means they depend on the thermodynamic processes. I will always write du to remind you again that u is path independent, depends on the initial and final state. Value of u depends on either initial state or final state. Du depends on the difference in initial and final state, difference in thermodynamic variables. So, isobaric process, pressure is constant, we can do this integration very easily. Okay. Take the pressure out of the integral, it is a constant. So, it is P V2 minus V1, it is simply P times V2 minus V1. And since I am talking about ideal gas, in both the cases its PV1 is equal to nRT1 in the initial state, PV2 is equal to nRT2 in the final case. So, it is simply given by the difference in temperature. So, I have kept pressure constant, okay. Volume and temperature, both of these quantities change. So, P constant, V and T change, and this is my net work done. I can write it expressing entirely in terms of change in volume or change in temperature, because I am using ideal gas and I am doing a quasi-static process. If I do not do any quasi-static process, I do a rapid change, I can go from one state to the other very rapidly, but I have to wait. Initially it was in equilibrium with P V1 T1, finally it may reach an equilibrium which is P V2 T2, but I cannot say work done is this, because I did not do a quasi-static process, rather I did a rapid change, and finally I have to wait for the system to equilibrate. Okay, this is another process. So, two thermodynamic processes we have already learned. One is isothermal process and second one is isobaric process. Let us go to the third one, isochoric process. So, volume is kept constant. I am not allowing volume of the container to change. Immediately I know that I am not allowing any work, no work. As I have written here, no work is done. Neither I am doing any work on the system, nor the system is doing any work on the rest of the universe. So, volume is kept constant. So, work done must be equal to 0. It is PdV. Okay. Work done, I again remind you, I told you integral PdV, this dV is 0. If dV is equal to 0, no net work done. Okay. So, the heat supplied to the gas is converted to internal energy. That is the first example I said, that I am supplying some heat. Okay. If you remember, this represents this situation I was talking about, that this situation where I said that delta Q, this or this, whichever notation you prefer, is the amount of heat supplied to the system, but there is no mechanical work, okay, which means there should be an increase in internal energy, which I am showing here, that there is an increase in internal energy. Recall the first law. Recall the first law, I was not saying delta Q and delta W are conserved. Okay. I am saying take delta Q, delta W and du if you like all together, and then you can have conservation of the total energy. That is my first law of thermodynamics. This is why internal energy is essential. Internal energy is essential to conserve the total energy. Heat absorbed increases the temperature and hence the internal energy. Remind you that I am talking about ideal gas systems. Internal energy is directly proportional to the temperature. If I supply some heat to the system, it increases the temperature and hence there is an increase in the internal energy. These three examples also establish that work done by the gas depends on the thermodynamic processes. So, amount of work I am doing depends upon the process. That is why this notation delta W, okay, depends on the path. Path means whichever process I take. The process could include or process could consist of two or many thermodynamic processes. Maybe first half is isobaric, second one is isothermal. We will see this type of multiple processes when I talk about heat engines or isobaric's. So, okay, when I talk about heat engine or refrigerators, these things will be clear. It could be, for example, isobaric plus isothermal, okay, multiple processes in going from one thermodynamic state to the other. Okay, this is an example, okay, and the work done will entirely depend on the process I have employed. What is important? Change in internal energy will be the same if I start from the same initial state always and reach the same final state always. It just depends upon the initial and final state, in precisely speaking depends upon the difference in temperature, since I am talking about ideal gas throughout. Okay. Now comes the final one. What is the work done in an adiabatic process? Adiabatic process is complicated. Here delta Q is equal to 0, that is important. Delta Q is equal to 0. That means delta U must be equal to minus of delta W. This is very important. W depends on path, okay, but du does not. So, if I have an adiabatic process, then W will be path independent. That is what I was trying to say. In mechanics, conservative force field, work done is path independent, brought in the concept of potential energy if you like. Similarly, here W is path independent, which gives the concept of internal energy. Okay. This is my delta W, which is P delta V, which I have defined. Now, let us recall, in kinetic theory we defined Cv and Cp. Okay. Okay, we used equipartition theorem, counted the number of degrees of freedom, and then we could easily find out what is the number of degrees of freedom contributing to the specific heat. And I used Cp minus Cv is equal to R for 1 mole of ideal gas, okay, and I said I will not provide any proof at that point. Now, it is the time we can look at it more critically. So, isochoric process, which means volume is constant. Remember, no work done, volume is constant. If volume is constant, I can define Cv. That is what calorimetry teaches us, that delta Q is the amount of heat, let us say, supplied to the system, and delta T is corresponding change in temperature. So, delta Q by delta T, keeping V constant, this notation means I am keeping V constant, let me go this way. So, this keeps V constant, this is du dt keeping V constant. Similarly, if you consider a process which is isobaric process, in an isobaric process you keep pressure constant. Okay, pressure constant. So, this is delta Q, heat supplied to the system, delta T increase in temperature, but pressure is kept constant, Cp. This is du dt. Okay. What is delta Q? Delta Q already we know from first law, as I have written there, delta U plus delta W, which is nothing but delta U plus P delta of V. I am writing delta here and consistent notation, same notation for Q, U and W, but never forget these two depend on path, whereas delta U does not. So, if I use this, pressure is kept constant, I want to take this derivative, pressure constant, and limit dt tending to 0, what I find out, since pressure is constant, first piece will come from internal energy, and then pressure is coming out, it is a constant, it is an isobaric process. So, delta V delta T holding pressure constant. So, this is my CV, this is my Cp, and I want to know what is the difference between Cp and Cv. This is important because what is our purpose? We want to calculate PdV in an adiabatic process. In an adiabatic process, temperature will not remain constant, temperature changes. It is not an isothermal process. If temperature changes, we immediately know there will be a change in internal energy also. So, change in internal energy because of change in temperature, and I cannot either use PV is equal to constant. I cannot say it is not an isothermal process. We know PV is equal to RT for an ideal gas, 1 mole of ideal gas. If temperature is constant, then I can say PV is equal to constant, okay? But it is not an isothermal process. So, temperature is not constant, okay? So, I cannot say PV is equal to constant. We have to be careful. Firstly, purpose is to calculate in an adiabatic process T is not constant, we cannot use PV is equal to constant, which is RT. Rather, for an adiabatic process, I must have some other equation, some other relation which is very important, which I am going to derive for you. This relation is PV gamma is equal to constant. Need not be the same constant as the previous one, a different constant, okay, which I will derive for you. Now, for an ideal gas, since we are dealing with ideal gas, we are lucky, okay, we are lucky. For an ideal gas, U is a function of temperature only. So, this derivative, if I write in derivative form, it is du dt keeping volume constant, but this fellow is a function of temperature only. Similarly, this is du dt keeping pressure constant. Okay. So, these two derivatives, since I am assuming internal energy as a function of temperature only, so these two carry no sense. Okay. Since internal energy is a function of temperature only, these two are same. Now, look at this equation. What you have? Cp, what is this quantity you are calculating? P delta V delta T, and you can immediately arrive at the equation. This is your Cp, this is your Cv, all you are left with Cp minus Cv is equal to P del V del T P, and if you calculate it for 1 mole of ideal gas, for which you already know PV is equal to RT, PV is equal to RT. If you calculate this quantity, this immediately gives you Cp minus Cv is equal to R. This is a very simple but very insightful proof of this relation, that for 1 mole of ideal gas, Cp minus Cv is always equal to R. That can be proved, I have shown in a very simplistic way. I repeat the proof. Cv is change in internal energy when you change temperature by a amount delta T keeping V constant. Cp on the other hand has P constant, so it will have a piece this and this piece this. This is the extra piece. Now, I am arguing that for an ideal gas, okay, I should always have this quantity equal to this quantity, this P and V which I have written here, they do not carry a sense, because for an ideal gas U is a function of temperature only. If that be the case, this first term Cp minus Cv, if you do, this term cancels with this term, all you are left with this term, and if you calculate using Pv is equal to RT here, you simply get Cp minus Cv is equal to R. So, first thing I have proved for you with some basic arguments, says Cp minus Cv is equal to R. Now, I have to establish this for you. I have not defined what is gamma for you. So, I have to define what is gamma, okay, and arrive at this relation. So, let us proceed. So, purpose is to know what is constant for an adiabatic process, as we know in an isothermal process Pv is constant. So, let us proceed. So, delta Q is 0 because I am talking about an adiabatic process. du is this quantity which can be easily found out, okay, with P delta V. Now, du I am talking about 1 mole of ideal gas. So, du is equal to Cv dt, that is what I have replaced here. You can easily see, remember Cv T plus constant, that is what I wrote as the expression from internal energy. This constant never matters, it is never relevant, because I will always talk in terms of difference in internal energy. So, this is important. Any thermodynamic extensive variables like internal energy, free energy, etc., we can always add a constant to that. You know, in classical mechanics, results do not change on where you set the 0 of your potential energy. So, Cv dt is minus P dV. This is simply from this equation. Once you set delta Q is equal to 0, it follows from the first law. So, I can write in differential form now, Cv dt is equal to minus RT delta V by V. What I have done? I have substituted P is equal to RT by V. Let me write probably here, P is equal to RT by V. Okay. So, I have Cv dt, P dV substituted for P RT over V, and already in the previous slide we have proved for ourselves that Cp minus Cv is equal to R. So, Cp minus Cv is equal to R, and you get an expression like this. I write it here again. So, Cv dt is equal to minus Cp minus Cv by V times T, and let us write also delta V in differential form to be consistent. Okay. So, this is the equation. Cv dt is equal to minus Cp minus Cv over V times T into dV. Okay. Everything is in differential form now, and now I can finally arrive at this equation. Now, I have intentionally not written where is gamma here. You can immediately see gamma is nothing but Cp by Cv. So, ratio of specific heat capacity at a constant pressure to the specific heat capacity at a constant volume. That is your gamma, that is Cp by Cv. Well, so this is the equation you have now. I write it again for clarity, dt by T is equal to 1 minus gamma dV by V. Now, you can integrate. If you integrate, you get this result. It is very simple integration. You always know dt by T, if you integrate, you get a log T. Okay? That is what precisely I have written here, log T 1 minus gamma log V plus some constant which comes from integration, and so that gives me T is proportional to V to the power 1 minus gamma. So, I have a relation in an adiabatic process. Okay? I can put it in more succinct form if I proceed, I had this relationship which was telling me T is proportional to V to the power 1 minus gamma, T is proportional to V to the power 1 minus gamma, or I can write T is equal to some constant time V to the power 1 minus gamma. Now use PV is equal to RT, because I am using 1 mole of ideal gas. 1 mole of ideal gas, I use PV is equal to RT. This relation is PV gamma is equal to constant. Okay? The question I asked, question I started with, for an isothermal process you have PV gamma is constant. It is a quasi-static process. At every instant of time it is in equilibrium and it is your PV is equal to constant. This is your isothermal process. What is the corresponding relation in an adiabatic process? Remember, adiabatic process is also quasi-static. But temperature is not constant. Rather, you will have PV gamma is equal to constant. Okay? For an adiabatic process, PV gamma is equal to constant. That is what we have to use when we want to do this work done in an adiabatic process. Okay? Remember, this constant, if I called C isothermal, this constant is C adiabatic. Okay? Maybe I can write this in the following way, that in an isothermal process, Pi, Vi, it does not refer to initial state, rather it refers to a process. Okay. Maybe to be precise, I use capital. Okay. So, Pi, Vi, that means isothermal process, is a constant Ci. For an adiabatic process on the other hand, you have Pa, Va, gamma, some other constant Ca. Okay? The subscripts here refer to the process, not the initial value. Now, if I give you two isotherms or two PV diagrams, not isotherms, I correct myself. Adiabatic process, temperature is not constant. So, I give you two curves, two PV diagrams and ask you the question, if one is adiabatic and other is isothermal, which one is isothermal, which one is adiabatic? I leave this question with you, and in the beginning of the next lecture we will come to that. That given two curves in the PV diagram on the PV plane, okay, I am telling you one is isothermal and one is adiabatic. You have to tell me which one is adiabatic and which one is isothermal, but by looking at the curves, or rather looking at the slope of the curves. This is a hint. So, our initial purpose was to calculate the work done in an adiabatic process. An adiabatic process is complicated. You are going from P1, V1, T1 to P2, V2, T2. Okay? Earlier, remember, earlier we were keeping one of them fixed. In isothermal process, I was having T fixed. Isochoric process, I was having V fixed. Okay? In isobaric process, I kept P fixed. But when I have an adiabatic process, all the thermodynamic variables change. But there is an important simplification. P1 V1 gamma should be equal to P2 V2 gamma. That is what I have proved for you. Well, now what is the work done? I have to calculate W, V1 to V2, and then PdV, which now I can write, since this is always satisfied. It is a quasi-static process, every instant this is satisfied, I can write it as C adiabatic, and then dV by v to the power gamma v1 to v2. Okay. Now, all you have to do this integral, and if you do this integral, you will find out work done. I am not doing the integral for you, you can very easily do that. 1 minus gamma P2 V2 minus P1 V1. This is the work done in an adiabatic process. Adiabatic process is very complicated because all the thermodynamics variables change, but keeping this constant, and that enables us to find out a closed form expression for the work done. Okay. And this is the expression for the work done, and now PV is equal to RT is always satisfied. After all, it is ideal gas. So, it is satisfied initially, also in finally. Okay. So, you can write this as R T1 minus T2 by gamma minus 1. Okay. This is the final answer, and gamma is always greater than 1 because Cp exceeds Cv. So, this is the work done in an adiabatic process, and I will come back to this in the next lecture. And what is the essence of today's lecture? I talked about work done by the gas and established for you that it depends upon the thermodynamic processes. Okay. Whichever process you take, it depends on the thermodynamic processes. For example, it is 0 in an isochoric process. Most complicated is the adiabatic process. I have given you an expression. In the next lecture, we will start again from the adiabatic process. Thank you for today.